I hope you had enough time to go through what we learned last week, because if we have time, we will try to do some quick revision on some past paper questions at the end of today. So if you have the prior knowledge, it will be really good. So let's focus on today's main topic. Today we are going to discuss about computer memory. Last day, we learned about something called the von Neumann computer architecture. Can you remember the main parts of the von Neumann design? Can someone type the main component of the von Neumann design to chat window? Or maybe you can verbally say it, since audio, you can unmute and answer verbally if you require. What are the main components in von Neumann architecture? We learned about two different things, von Neumann and the Howard architecture. There are several important components. What are they?
Processor.
Hello? I heard someone answering, but the line was not clear. Processor, yes. Processor is one important component. What are the other things? Second answer should be fairly easy because you already have it in the slideshow. Right? You already have it in the slideshow. The memory is another important component. So other than processor and memory, what other things are there in the von Neumann design? Input-output facilities, yes. So this is the Neumann design. You can see we have the processor, we have the input-output facility, and we have the computer memory. In addition, you have a system bus which connect all these components together and allow them to communicate with each other. That day we learned about the computer processor. Today we are going to learn about the computer memory, another very important part in the computer architecture. So memory, or in other words known as the storage, is a way to store the information. You can write some value to the memory and you can read it back later. Can you remember the basic unit in electronics that could store a single bit? There were several units that could have been used, but can you name one of them? In the electronic circuit designing, we learned there are several components that can be connected together to create a memory module, a simple memory module. What is the simplest unit that you know that can store a bit? There can be multiple answers because there are several circuits that could store a single bit. But can you name one? Flip-flops, yes. Flip-flop can store a single bit of data. Okay? But today we are not going to discuss about the electronic part. We are basically going to discuss it as an overall process. Okay? Now, there are two different things we are going to study when we are studying the memory. First, we will look at the physical structure and how it can be, how the performance can be improved. Then we will look at some abstract concepts, right? Like how certain policies are made and things like that, which will give you an understanding how it functions. Right? So there are two components for today's presentation. We'll start with the easy one, the physical structure, or actually how the memories are built. Now, depending on how the memories are used or built or different requirements, you can categorize them in different ways. For example, you can categorize them based on the power requirements, access mode, and type of media that is used, and so forth. If you look at any of the common use memories like RAM or USB drive or something, they will probably fall into more than one of these categories. Right? So let's start with something like this. Power requirement. In memory, you have two types of memory categories, non-volatile memories and volatile memories. A non-volatile memory is able to keep its data even without the power. So you don't need the power to retain the data. For example, if you look at the computer hard disk, even when you switch off the computer and remove the plug from the power supply, it will still keep all the files. So it's an example of the non-volatile storage. Similarly, if you look at a USB drive, a USB drive doesn't have a battery or anything, but it's still able to store the data. On the other hand, certain memories are called volatile memories. In the volatile storage, you need constant power to keep the data stored. Example would be the RAM. Now you can only keep the values or variables in the RAM as long as you have power to the RAM. So think of this scenario. You are writing a Word document, you save it, then you type some more and the power fails, computer shuts down. What's going to happen? The part of the document that you had saved earlier will be available for you. But any editing that you didn't save might have been lost. So the reason is the document was originally at the RAM and all the editings and changes were at the RAM. When you say you are saving, what you are basically doing is you are moving that information from volatile memory to non-volatile memory. So once you save it, copy of that document, copy of that uh, particular instant was copied to a non-volatile memory or to the hard disk. So even when the power failed, that copy remained. So you could recover it. But whatever changes you made to the RAM and was not saved would be lost. Because RAM can't keep the data when there is no power. Okay, you can think of RAM is more or less like a feedback loop, so it needs to refresh it very frequently. So without the power, it will not be able to refresh, and you will lose the data. So that is one way of categorizing the memory: non-volatile and volatile. Then you have the access mode. Access mode means how you can access a particular given data, a particular given point in the memory. In the sequential access, you can't directly go to a given point. You have to go to it page by page or one step at a time. If you're at the location 10 and you want to access something at location 20, you have to go to location 11, 12, 13, like that. It is more or less like a cassette. I don't know whether your generation had seen cassette, but you can see an image of a cassette here. So if you want to go for a different song in a cassette, although it looks like a cassette, I think it's a magnetic tape or server storage or something, but cassettes are look almost the same. So if you want to go to a particular song, you have these two buttons called fast forward and rewind. You have to press them and wait until the tape moves to that given particular location. You can't skip and directly go to a different place. But if you look at something like a modern MP3 players, they have a different scenario. You have a playlist, you just click it and it will directly go to that particular one. So that kind of access is known as random access. If you have to go through all the data before going to the particular place, it is known as the sequential access or the SAM. But if you can access any point at random, that is known as the random access memory. Now, for example, flash drive or RAM, they are good examples of the random access memory. And things like tape drivers are good examples of the SAM. Now, SAMs are used quite in the cases of backups, because in the backup, you don't regularly need to access different points. You just want to keep a point, record the data. So in that sense, SAM is cost effective, like a tape drive, and you can store them. But in the case of using a computer in the way that we are using today, where you need to access different files from different locations and things like that, RAM is commonly used. Then we come to another category. Now these first few slides are basically background. So you just need to remember certain facts. There's no calculations or anything available. Now some of the memories are called read-only. That means you can write to them once or maybe one or twice or few times, but you can't write to it multiple times. However, you can read them multiple times. A good example would be a CD or a DVD. Now, if it is not a rewritable CD, you can burn a CD only once. So if you want to record some movies or maybe songs or something, you can burn it once, but after that, you can't use it. But if you want to read that song or whatever the data, you are able to read it multiple times. Such things are known as the read-only memory or the ROMs. It doesn't have to be optical devices. There are even some chips that function like that. Even some microcontrollers, there are some microcontrollers that allow you to burn the program only once, but not allow you to erase it. In early days, we had some BIOS chips. Now, BIOS stands for Basic Input and Output System. It's a part of the computer where you boot the computer early, that display all the information. So that basic characteristic and everything, basic characters and all that things are handled by the BIOS. So there were early times where the BIOS chips were read-only. Nowadays things have changed. So there are chips also that are read-only memory. However, things had changed since then. After a little bit of time, you got UV erasable chips. Now in the second image, you can see a UV erasable chip. You can see the chip is the place where you have a chip, you have actually a glass window. Now, using the UV light, you are able to reset the bits in this particular memory. The UV rays excited the UV rays erase the parts of this memory. So you can, in a way, erase it and rewrite on it. Later on, this changed a little bit further, and we had the opportunity to see the chips that can be erased electronically. So these chips are known as EEPROMs, or electrically erasable and programmable read-only memories. Now, whether it's actually read-only memory is something like a debate, because the wording itself says read-only, but on the first part it says erasable. But if you look at something like a USB drive, they are basically like EEPROM. You have EEPROM chips inside it. And if you're using microcontrollers, you have EEPROM ICs where you can store values. So those things are called ROM, but they can be erased and programmed back using electrical signals. Next category I am going to share is how you can categorize them based on the medium. Now, can anyone identify what is this photo? What is shown in this photo? What is this one? Any suggestions on the chat? Yes, it's a punch card, a very early storage medium. So in early days, when you need to input some data into the computer, they use punch cards. So it's a set of a hard paper of sheets or something that had a list of numbers, and you can punch each of the numbers to give some information, right? So it's quite similar to that hand loom device that was designed by the Jaeger, because it again used punch cards. But this is one of the earliest storage mediums. Then we have optical devices like CDs, DVDs, and things like that. We have magnetic devices like hard disk and floppy disk, if you know what I mean, what is a floppy disk. And we already have electronic storage medium as well, like solid state disk and things like that. So depending on the storage medium, you can categorize them also. So those are some backgrounds of different memory types. You can have different memories like that, and they can be in multiple categories. For example, if you look at a CD-ROM, it's an optical device, and it's also a read-only device. If you look at a hard disk, it's a magnetic device, and it can actually access randomly at any location. So you can see there are different categories. The same device can be in multiple categories. Now we will move to a different topic. So far we learned there are different types of memories. CD-ROMs, hard disk, things like that, RAMs, things like that. So they have their own advantages and disadvantages. One common theme is if you have a high-speed memory, that means it can write or read data very fast. Usually the cost is high and it will consume a lot of power, and also the size may be a little bit large. So that's something like a quite common thing. On the other hand, you can build certain memories like hard disk, which can store a lot of data, and they are quite cheap, but unfortunately you can't read or write data fast as the other type. So you have sort of like this spectrum. Yeah, you have expensive and fast memory, and cheap and large but slow memory. So we have to consider all the facts when we are building a memory and using this, when we are building a computer and using the memory. Now remember, in the computer architecture, we are thinking not only about the technical aspect, but also about the economical and things like that. Now ideally, if we can build a computer that consists only of the fastest memory, that would be great. That means it can work very fast. But it is not practical. The reason is, if you want to store a large amount of data, you need to buy that storage. And if you're going to buy the fastest storage, then it's going to cost you. For example, think about a normal computer. Now, computer can have usually about 1 terabyte or 2 terabytes of hard disk. So that will cost about, if you're using SSD or something, I think about 10,000, 15,000 in that scale rupees. But if you look at the RAM, now you can't buy 1 terabyte of RAM, not in the local market, I don't think. Usually RAM goes by 8 GB or 16 GB sticks. So if you put several, then maybe you can go up to 64 gigabytes. But that will cost you a lot more than a 1 terabyte hard disk. So in one hand, you have 1 terabyte, which is costing less. And on the other hand, you have a RAM, which is much smaller than the hard disk, but cost much higher. So it's clear we can't build a computer with things like RAM, only with RAM, and expect it to have very large storage. On the other hand, we also need to have a large storage. For example, if you want to store all the films or songs or things like that, they will consume a lot of memory. They will consume a lot of storage. And even a modern day software like MATLAB will have about 10 GB. And if you look at SolidWorks, or even things like operating system itself will consume a lot of memory. So we need to find a balance between making the computer fast and making it able to handle or increasing the capacity to store large amount of data. So that is where the memory hierarchy comes in. So the idea is this: although the computer might have a lot of data in it, we will not need to access all of that data frequently. For example, you might have some photos of your past trips or your friends or school times or things like that. Now you're not going to access those photos every day, every time, right? You infrequently access it. And there might be certain programs or things that you access quite frequently. Maybe you are writing a report these days. Right? Then you need to access the Microsoft Word and that particular document maybe 1 or 2 times a day. And if you're using something like Internet Explorer or Firefox, or maybe using Facebook, then those things need to be accessed quite frequently. So we can see some parts of the memory are quite frequently used, others are not that frequently used. The solution proposed by the memory hierarchy is as follows. You will have a smaller amount of very fast memory, and you will have a very large amount of a much slower memory. The things we will be accessing frequently will be uploaded or stored in that fast memory. So you can access it quite fast. things we don't access quite frequently will be stored in that slow speed but larger capacity. So you have the storage, enough storage to keep them. If you need to access something infrequently, then you have to wait a little bit more because you have to get access from the hard disk and upload into the working memory. So that's the basic idea of the memory hierarchy. But of course, it's a little bit more complicated. And instead of having just two layers like fast and slow, you have several intermediate layers. So this is a typical diagram of the memory hierarchy. It's a pyramid. So the things at the top are fast. When you move upward, things get faster, but also more expensive. When you go downward, things get cheaper and have a larger capacity. Some diagrams may not have this last layer, which is the external storage, but most of them will have up to this particular triangle. So if you look at the top of the pyramid, you can see at the very top you have something called CPU registers. That day when we are discussing about the processor, we learned the processor has three components. Can you remember the three components? Can you type in the chat what are the three components inside the processor? Three, or if you consider the internal bus and the external interface, you might have more than that, but three main components are there. What are they? ALU and control unit, yes. What else? Registers, that's right. Now, that day I mentioned registers as a part of the memory. That is because of this particular reason. Registers are, in fact, a part of the memory. They basically store and retrieve values, but they are inside the processor physically. The reason is the memory hierarchy. Now, registers are able to store small amount of data, but they are very fast to access. So let's say a processor is doing a little bit of computing and you want to store the results or get some new values there, then the best place to store those things are in the registers. So they are very fast but quite small. You can't store much in the registers. After that, you have cache. Now, cache comes in different levels. Usually you have two levels of cache, but in rare cases you can have three levels of cache. Now, the location of the cache again can vary. Usually the first layer of cache is inside the processor itself, but things like level 3 cache sometimes can be in the motherboard as well. They are usually in the megabyte range, not quite large, but relatively fast. Compared to registers, they are slow, but compared to hard disk or anything, they are fast. So that's the second layer. Then you have what is called the main memory or the RAM. When you call about the memory, usually what you call by default, you are thinking about the RAM. Right? Then you have the RAM. Now RAM have two components, physical RAM and the virtual memory. We'll talk about the virtual memory later on this session. So that's the next layer. And then you have the secondary storages. Things like hard disk, USB drives, external drives, and things like that. So this layer is quite small, quite slow, but can have a lot of capacity. So is it clear about this particular hierarchy? Now this last layer you can neglect. It's basically when you need to connect external components, they might have their memory as well. Like for example, if you connect a camera, something like that, that again will have a certain amount of memory. But when you consider a computer, the first 1, 2, 3, 4, these layers will be sufficient. Do you have any questions? Uh, obtain memory. Where do you find that word? Obtain memory. Is it in my diagram or are you talking about the obtain processor? I think you might be asking about the particular. Right, right. So in that case, I think you are referring to this one, this m.cache, m.2 thing, if I remember. Now, I'm not quite sure. So what I think is instead of what you are referring to obtain is probably the m.2. So instead of using hard disk, you have a new technology where you use solid state devices like chips, right? So they can be connected directly into the PCI Express slot, which is a very fast bus lane. So rather than going through SATA or everything, you can use that as a secondary storage. So that will be much fast, but not fast as the RAM, and but will be faster than a hard disk. Now, let me show you something else. So this is my personal computer, this laptop, and there's a small free program called CPU Visit where you can check different properties of your computer. So here I'm checking the properties of the CPU. You can see there's something. This is the CPU, so it's an Intel Core i5. So you have several things like that. What I'm mainly interested is about this cache. Now you can see there's a level 1 cache. So it's 32 kilobyte. So it's a very small. And you have level 2 cache. You have about 256 kilobyte. And this one has a level 3 cache as well. So it's about 6 megabytes. So you can see as the level goes down, the amount of cache increases. But at the same time, the speed will decrease. Okay. So that is basically about the memory hierarchy. Now let's look at how a memory can be accessed or data can be written. I'm sure you remember we built a small memory using digital gates. Now in that case, we had 3 different control signals. We had data, we had address, and we have a control signal to decide whether to write data or to read the data. So we'll forget about the physical circuit for the time being, and we'll consider about this particular diagram. So this is a design of a working memory. So you can think of it like a table. You have address here, and you have the data. Now, if you want to access a particular data, let's say data number 3, you have to find that particular address and access it. So if you want to store some value at this particular location, you have to say store this particular value at the address of 1203. Like that, the address is the key to writing or reading values. So the address has to be unique. And in addition to address, you have 3 more data buses. Address bus, data bus, sorry, with the address, you have 3 data buses, address bus, data bus, and the control bus. So memory address is the place where you are going to read or write values. Right? It's like address of a house. So if you want to deliver a letter, you have to know the address, so the letter will get delivered. Similarly, if you want to write some value to a particular memory location, you have to know its address. And data is like the actual content of the letter, or what is need to be read or write into that particular location. Control instructions decide whether it's a write instruction or a read instruction. So there will be 3 buses that we will be discussing later on the next session when we talk about I/O streams. So these three things are there. Now let's do a little bit of calculation about how to find the memory storage capacity. Now, amount of memory that can be allocated, all possible memory allocations, is known as the address space. Now remember, everything inside the computer is binary. So even the memory address should be represented using a binary set of numbers. Now let's say you have two bits of uh, 2 bits to represent a memory address. Then there are only 4 possible combinations are there. Similarly, if you have 3 bits, you can see in the example, using 3 bits, you can have 8 different unique combinations. Since each address needs to be unique, you can give 8 unique different addresses using 3 bits. Now you can expand it to the n number of bits using this particular formula. 2 to the power n will give you the number of address. So in this case, you have 8 addresses. What about the actual capacity? Now remember, this is just the number of addresses. The actual data is stored here. So this one can have different capacities. So the capacity of this one particular memory location, capacity of a location, this memory location is known as the word size. It's known as the word size. Usually, the word size is taken as a multiplier of commonly used data type. Let's say ASCII, ASCII has 8 bits. Then Unicode can have either 16 or 32 bits, like that. So they are all multipliers of 8. Reason is, if you want to access this particular location, you have to access all that data from that location. So you can't store part of the variable in this first part of this particular location and part of it in this other part of this location. So when you are giving address, you are basically accessing all the data in that part. Okay, I'll be honest, that is not strictly true. There's something called byte addressing, but it's out of your scope. So we'll not talk about the byte addressing. So for the time being, you can imagine when you give an address, you will read or write the whole word size, whole thing in this particular location. So it makes sense to make it a multiplier of the commonly used data types. For example, let's say you are using, you are typing a document in ASCII. So every character has 8 bits. If your word size is 9 bits, you are going to waste 1 bit because you can't store anything there. 8 bits are stored there. 1 bit is there, but unfortunately, it's in the same memory location. Similarly, if you have 7 bits, you have a problem of storing the 8-bit data. You have to use 2 slots. You have to use 2 memory locations. So most of this time, you will see it's a multiplier of 8, 16, 32, like that. Now let's do a small calculation. Now remember, using the number of bits in the address, you can calculate how many unique addresses you can give. And for each of this unique address, you will have a place to store the value. And the size of that storage is known as the word size. Now remember, word size is per address. So if you have 8 addresses, you will have word size for each of these. You will have memory capacity of a single word size for each of these locations. So if it's a word size is 8-bit, you can store 8-bit here, another 8-bit here, another 8-bit here, another 8-bit here, like that. So here's the exercise. You have a 32-bit computer, so you can assume the address size is 32-bit and word size of 1 byte. Word size is 1 byte. What is the maximum supported memory for this given computer? Can you do a quick calculation? So I can give a hint. First, find how many unique addresses you can give. Then for each unique address, you have a capacity of 1 byte. Then how much is the total capacity of the memory? Can you do a quick calculation and give me the answer? You can do the unit conversion. You don't have to give the answer in bytes. You can give it in megabytes, kilobytes, gigabytes, terabytes, whatever the bytes you feel like is most suitable to represent the value, right? I'll give you a few minutes. Can you very quickly do that particular question? Okay, I have received one answer. We'll see whether it's correct or not. By the way, this is from my other computer. I did a little bit of VNC, and you can see in this processor, you have a different amount of cache. So you can see the cache here, 32 KB, 32 KB, but this one has about 6 megabytes of cache in the L2. L1 you have 32 cache for the 2 cores, but for the L2, you have different amount of cache, right? You can see for different processors, you have different amount of caches there. Anyone else finish doing that calculation? Is it hard? Okay, how many bits are in this particular address? When the question says it's a 32-bit computer. To be honest, your address size may be slightly changed on other facts. For example, all the 32 bits may not be used as a memory address, and in some cases you can even extend it even further. But for the simplicity, we'll access this 32-bit is the same for the memory address as well. So your n is 32. How many unique addresses you can get? Number of unique addresses will be 2 to the power 32. Then what will be the total capacity? So we have this amount of memory location, and each memory location can contain 1 byte. So 1 byte into this number will give you the total capacity. But of course, this looks a little bit larger since we are given in bits, given in bytes. We can convert into something more manageable. How many bytes per 1 gigabyte? In 2 to the power kind of notation, 2 to the power how much? So you remember the cycle, right? You have 2 to the power 10 for the kilobyte, megabyte, then you have the gigabyte. You have 2 to the power 30. So we can simplify it quite easily. 2 to the power 32 divided by 2 to the power 30 is in gigabyte. So you can effectively have 2 to the power, sorry, this 2 should be there, only 30 should be there. Let me rewrite it. I should get confused. 2 to the power 32 divided by 2 to the power 30 gigabyte. 30, you remain it 2, so that gives you 4 GB limit. Now, if you remember, we have saying that upgrade to 64-bit, otherwise don't use too much RAM. Now, this should give you an idea why it is so, right? Because you have a theoretical limit. The actual limit is even slightly less. But if you upgrade to a 64-bit machine, then you have a higher memory address capacity. That means you can put more memory into your computer. So that's one exercise. Is it clear for you? You should be able to do such calculations by yourself. Right. We'll now move to the next one. Have you done C or C++ or anything that has the word pointer in it? Any programming language? Pointers, have you used the pointers? Good. Now, when you're starting the programming, it feels a little bit confusing. What is this pointer? Why you put a asterisk at there, and why it is meant by calling by reference and all these things like that. So this part should explain why it's like that. Now, I mentioned earlier A memory basically consists of two components. You have the address, like this, and you have the values stored. As long as you have the enough capacity, you can store any binary pattern in this capacity, in this location, in these locations. Right? So it can be integers, strings, characters, whatever you like. One special case is you can store an address, you can store another memory address in these locations. So instead of having the actual data, you can store a pointer or a link to another memory location. That is what is called a pointer. Now here's I have an example. You have the variable A and the register address, memory address associated to that particular variable is 002. So you want to access the variable A. So you go and find this particular memory address and look into its content. Now, instead of finding the actual content of the variable A, you find another memory address. In this case, the memory address is 1008. So to find the content of A, you have to go back and find the address 1008, and whatever in that location is the actual value that need to be used for the memory, used for the variable A. So you can see when we are accessing this particular location, it points to a different location. So such a thing is known as a pointer. So a pointer has its own hardware kind of implementation. Rather than using the value directly, you will be pointed to a different location. It's like a diversion of a call. When you give a phone call, sometimes you can divert it, something like that. Is it clear about the pointers? Now this particular chapter will have several smaller subtopics put together. It's not like a one large one. You have several subtopics going here and there. So point is one such topic. Is it clear what the pointer is from a computer architecture's view? Okay, next small subtopic, memory banks. How many of you had learned microcontrollers, maybe PIC or something? Have you done any programming using assembly, where you are referring to bank 0, bank 1, and something like that? Maybe you have, maybe you haven't, I don't know. In the previous years in your degree, have you referred to something like that? No, okay. Then we'll start from something beginning, right? If you remember, in the NEUMANN structure, you have the processor, control unit, you have the processor, memory, and the input outputs. Now the data and instruction and everything need to be fetched from the memory into the processor. Usually, if you have a single controller for the memory, you can only fetch a single value from at a given time. Can you remember a small design for the memory access? We had multiple registers, then you have a multiplexer and a demultiplexer, and you have a decoder and an encoder. So in that case, you could access only a single value at a given time. You could only read or write a single value at a given time. But some architectures allow you to access multiple values at the same time and do the work parallel. That will increase the efficiency. For example, let's say you want to add two numbers. Two numbers are in register 1 and register 2. In the conventional way, first you have to fetch number 1, then you have to fetch number 2, and then you have to do the addition. But it can be much faster or efficient if you can fetch number 1 and number 2 from the both registers at the same time. That way you can save some clock cycles. But to do that, you need to access the memory at the same time, two memory locations at the same time. In other words, you will need to have two memory control units. In other words, you have to partition your memory into separate banks. So each of these banks can be accessed parallelly, independent of each other. So that is the idea of memory banks. So some microcontrollers explicitly say if you want to add two numbers, those two numbers should be come from two different banks, because one side of the ALU is connected to one bank, let's say bank A, second side is connected to bank B. So you can't add two numbers on the bank A at the same time. You have to transfer it back to bank B and get them together. But what it allows is, if you had programmed it correctly, you will be able to put most of the numbers divided between the two banks. So at the same time, you can load numbers from the both banks. So with the one go, you are able to access multiple data or instructions. Right? So that is the idea of having memory banks. Again, it's a very small topic, but I hope you got the idea. If you have any questions, please let me know. Because this next topic is going to be a little bit lengthy, but it's a very important topic. So if you have any questions regarding banks or pointers or memory space, memory address, or anything like that, this would be the time to clarify them. Because this next topic will going to take some time, and you need to understand it in quite clearly. Any questions? Yes, no, maybe. When you don't have questions, that either means you had understood everything or you had understood nothing. Because if you understood everything, there's no question to ask. If you had understood almost nothing, then you don't know what to ask. So which one is that? One person says it's understood. Let's move to another very important topic. This is called virtual memory. Remember, at the beginning of today's lecture, I mentioned there are different types of memories. They can be sequentially accessed, they can be randomly accessed, they might be volatile, non-volatile, they may have different speeds, and all these things are there. Now, when the controller unit or the processor want to access a memory, it should not have to worry about all these differences. Right? If it want to store some value, it should be able to store that value at given location easily. If you want to get some variable from a memory, it should be able to get that value from the memory. It should not be that troublesome for the processor to figure out all these things and do it, right? So that's why we create something called a virtual memory. It's like an interface where all the memories are brought together and provide you with a unique interface. It's not a real memory. It's not something you can touch like a RAM or hard disk. It's not tangible, it's just a concept. So when the processor want to access something, it will access that value from the virtual memory, and it's the function of the virtual memory to find the real location or hardware location for that particular address and do the necessary reading or writing. So this have many advantages, right? Mainly it simplifies the memory management, and also the programmer or the processor doesn't have to worry about the underlying hardware differences, right? So here are some of the main advantages. By the way, before going that, this is an example of how it happens. Now you can see here you have a RAM, here you have the hard disk. So let's say this is one location in the RAM, one or several locations, and you have another place where you can store values, and you have another place in the hard disk. But when you access in the virtual memory, you only see the addresses. So this one is actually in the RAM, while this particular data is actually in the hard disk. And this particular data is again in the RAM. But when you are accessing the virtual memory, you don't care whether it is in the RAM or hard disk or the USB drive. You just access these locations, and the virtual memory manage and find where they really resides, where they are actually stored, and do the necessary reading or writing. So the first obvious advantage is the homogeneous integration of hardware. That means different hardware and different memory technologies are used together, but for the processor or the programmer, they provide a very uniform interface. So you don't have to worry about all the inside details. You just write for that particular virtual memory and it handles all the underlying complexities. That's also part of the programming convenience, because you don't have to worry about whether the data is written, whether the hard disk is busy, whether the CD-ROM is there. These things you don't have to worry. And it supports multi-programming. We'll cover this in a little bit next slide, and also the protection of programs and data. They go together. So we'll cover them in the next slide. So is it clear what the virtual memory is? So when you're looking at the virtual memory, you're actually looking at different types of memories brought together and provide a consistent interface for the processor to access. So the processor don't have to worry about all these differences. It just need to worry about this particular virtual memory. Is it clear? Right. Now let's look at another very important concept, another very important advantage of virtual memory. It is called multiprogramming. Now, you know, in today's world, you have program in the computers, you have multiple programs running at the same time. At first glance, it's look quite easy, but when you start looking at underlying structure, you find there are several key problems to be tackled before you are able to do that. For example, let's say you have a program, let's say program A. Now in the program A, I have A is equal to 10, B is equal to 20, C is equal to A plus B. And you have another program. Now another person is writing another program. He says X is 5, Y is Z, sorry, not Y is 2, Z is equal to X minus 1. And let's say you write this program and compile it. Now remember, these are variables. The way variables are stored is you will map each of these variables to memory location. So A, let's say address of A is 001. Compiler decided this is the first memory address. So let's allocate the first memory location for this one. So this is the address, and the value of that address would be 10. Okay, you have to write it in binary, but I'm being lazy. I'm just writing the value in decimals. And the memory address for the B would be 002. It's 20. And C is memory address 3. You have to fill the value and the process will fill the data. Now let's say you have another program and he also compile the program. And let's say this is somewhere, there are several lines above it. So compiler decide X should be stored at memory location 2. This is the value. Y should be stored at memory location 3, and this is the value. And Z is to be stored at memory location 4, and the CPU has to store the value, right? So if you just look at this single program, it looks there's nothing wrong. You have all these memory locations. The computer will do all the calculation and store the value in the third location. Then you can retrieve it. And if you look at only this particular program, again, there's nothing wrong with it. you have all the variables and you have all the relevant memory locations allocated to it. So memory location 2 is X, 3 is Y. So whenever you say X, you will refer to memory location 2. Seems quite okay. But the problem comes when you try to run both of these programs same time on the same computer. Why? Now what's going to happen? Remember, you have only single memory. So this is the address. This is the value 001, 002, 003, and 004. Let's say in one clock cycle, this particular thing works. So you get value 10 stored here and 20 stored here, and this one is pending. And while this is processing, the user switched to the second program. Maybe he thought, okay, this is going to take a long time. While it is being processing, I'm going to run this other program as well. Now what's going to happen? Now at the first instruction, it says store the value 5 to the memory address 2. So the process is going to store value 5 to the memory address 2. And this one will be stored to the memory address 3. And this one will be pending. And let's say the user then decide, okay, I'll come back to the program and see what's going to happen. Now the program A knows the value of this calculation should be at the memory address 3. So he goes back and check the value at the memory address 3, find the number 2 and thinks, okay, the answer should be number 2. The answer is number 2. But is it the correct answer or has something gone wrong? What do you think had happened here? Do you want to explain that a little bit again? Yes, the answer is wrong. What happened here is this program had certain memory addresses and certain values to be written or read from those memory addresses. This second program again had a set of memory addresses and values to be read and write. Unfortunately, there was an overlap between these two programs. So while this program is writing to the memory, other one also came back and write to the same memory locations. So the answers for the both programs got corrupted. So this kind of thing can result in a lot of problems. One thing is as obvious, it can give rise to the wrong answers. It can clash programs, but most importantly, it can be also a security flaw. For example, let's say you are storing the password at the memory location C. We have the password. So the password is stored at this particular memory location. Then someone can write another program to access this particular memory location and retrieve that particular password. Similarly, another program can come and inject some wrong values here so that original program functions differently. Maybe it can be a virus or something that comes into that one, infect the RAM and change the functionality of the program. So it is clear this kind of approach is not going to work. So what is possible? Can we start from 20 and write things like 22, 23, 24? You can, but unfortunately there are so many unlimited number of programs, you can't guarantee to always find a unique memory address. And also that will means if you have something like, let's say 520, 523, 524, your memory needs to be as large as that. So this approach is not going to work. But the virtual memory had solved this particular problem quite intelligently. So this is what our virtual memory management does. Let's say this is program A. In the program A, we had, let me write it in new paper. Program A, you had A, at 10, B at 20, C. Yeah. So A is translated into 0, 0, 1. So this is the value of A stored here. And 0, 0, 2 stored the value 20, 10, 20. And 0, 0, 3 stored the value what is calculated after that one. Similarly, for the program B, you had 0, 0, 2 with the value of 5, 0, 0, 3 with the value of 2, and 0, 0, 4. You have to subtract and fill the values. So those are the two programs, program A and program B. They both try to access this memory location 2 and 3. So there is an overlap. What the virtual memory does is, it doesn't actually give you this particular address. It takes the program. Let's say this is the program A. It says it wants to access this particular memory location 0, 0, 1. Now what the virtual memory does is, it adds a constant to this particular starting value. Let's say 5. So the 0, 0, 1 is now translated to 0, 0, 6. And that is the place where you are going to store the first variable of this one, 10. Then the program may access the second variable, B, value is 20. Again, it will have the same constant, so it is mapped to 0, 0, 7 and 20 is stored. Similarly, 0, 0, 3 plus 5, it becomes 8, and the value to be calculated here. So the values are calculated here, and the processor can do the calculation and get the value 30. And when it is returning, it will subtract this constant, and for the program, it will look like the memory address 3 is giving the answer, because you are adding a constant, and when you're adding a constant, when you go this direction, and subtracting the same constant when you are coming back. Now let's say you are trying the program 2, program B at the same time. Now the program B is accessing memory address 2. Now the virtual memory will do the same thing, but this time it will at a different constant. Let's say it at 10. So in the real memory, the memory address 12 will be the place where this value is where this value is stored. While the program thinks he is accessing the memory address 3 or the register 3, the real location will be 13. And when he wants to retrieve the value 4, value at the registry 4, it will be actually getting the value from the registry 14 and converted back and given us here. Now you can see there's no overlapping, right? In the original memory, or sorry, not in the original memory. In the memory, now you have 6, 7, 8 allocated for the first program, 12, 13, and 14 allocated for the second program, and there's a gap also. And there's no clash, there's no overlapping. You can't access data of this program and you can't access data from this program. So they are bounded. But for the original program, it doesn't see the difference. When it says every time it gives you a memory address, we will add a constant and store it. And when every time it asks for a value, we will add 5, go that location, get the value and subtract 5 and give it to the correct address. So there's a conversion happening. Using this conversion, you are able to remove that overlapping functionality. So it improves the security and the reliability of the programs. And also, it makes programming much easier. So that means you can start using from the first register. You don't have to worry anything about other people or other programs using certain registers. You can always start with the first register and continue to use the rest of the registers. This particular virtual memory manager will manage the conversion and map it to like this. So the starting place is known as the base of the particular program. So let me show you. So here you can see, here you have a memory space allocated for the program A. Start from 15 and finish at 90. So it was only provided 4 memory locations. It can't access anything more. Right? So the base of this particular one is 15 and the bound is the size, bound is 4. Remember, bound is not 19, bound is 4. Similarly, for the second program, you have a base of 24 and a bound of 6. So this program can use registers. In the original program, you might be using registers 1 to 4. This program might be using registers 1 to 6, but there's no clash because the base is different. So you are adding a constant and shifting it. Therefore, there is no clash. Similarly, this program can only access things inside its bound. So if this program, the first blue program has, let's say, a password, the second program can't access it because it doesn't know the address, and even if it found out the address, the memory manager will only allow it to access what is dedicated to its memory space. It can't access anything outside that box. So that way, it improves the security of this particular, it improves the security, right? Is it clear? This is how the multi-programming is supported by the virtual memory. Is it clear? Okay, these are some advantages. Using base-bound registers, you can have multiple programs running, and it also improves the security, and also it makes memory management much easier. Now we'll move to the next larger topics. There are only 2 larger topics. Next one is the cache. Now when we look at the memory hierarchy, we saw there are certain levels, there are different levels of performances. At the top you had very fast ones, at the bottom you have very slow ones, and somewhere in the middle you have the caches. So what is the function of a cache? Now the function of the cache is to make the frequently available data or instruction for fast access. Okay? So it tries to predict what is going to be accessed next and store it in the cache. So when the processor asks for it, it can quickly give it. For example, if you have something like a loop structure for I equals 1 to something, the variable I will be frequently accessed. So if that value needs to be retrieved from the hard disk, it's going to take a long time. If it's in the RAM, again, it might take a certain amount of time. But if it's in the level 1 cache, that means it's almost close to the processor, and it can have a very high access speed. So when every time it calls for the variable I, immediately it can give you the value. So that's the idea of the cache. Now there are several characteristics of the cache. First, it is very small. You don't get large cache, maybe several megabytes at most. And it's active. Active in the sense it's actively checking the values, what values have been accessed, and updating the cache and things like that. It's not a passive thing, it's actively changing the values in the cache. And it's transparent. Transparent means when the processor asks for a particular value, particular variable, it doesn't care whether it's in the cache or not. It just asks for that one, and the cache, if it has it, it will give it. Otherwise, it will go to the RAM, fetch it back, and give it. So the processor doesn't know whether it's directly accessed from the cache or whether it's accessed from the RAM or whether it's from the hard disk. It doesn't know, and it doesn't care. So it's transparent. Only thing it needs, only thing the processor asks is give that value, and the value is given. So the cache is like a transparent, although it's there to help you increase the performance. In otherwise, you can't see it. You just ask the value and it's there. Whether it's the cache does not do any other data manipulations, right? So it's transparent. And cache is automatic. So the cache has its own way of deciding what to be replaced and what to be kept in the cache memory. So here's an example of how the cache works. If you don't have the cache, every time you ask us something, let's say you want to get the variable X, You have to go to the storage, let's say RAM, and get the value. So it takes a long time. But when you have cache, you have this intermediate storage. It's high speed but small, and it's also temporary. So when you ask for the variable x, it can go there, and if the variable x is there, it can give you a local copy of the x. And you can do the processing and store the variable x. Again, it will be there. If you ask for x again, the updated value will be come here. So you basically process like this, and time to time, you will be writing the value back into the main memory. And sometimes you might need to retrieve value from the memory. Let's say this one asks for the y, and the y is not in the cache. Then you have to fetch the value from the memory to this cache and then retrieve to the processor, right? So here's a small example of how the cache can increase the performance, right? Now here are a set of instructions in the program. You read x, then you do something to x several times, and you store the variable x. This is the case when you don't have the cache, and this is the case when you do have the cache. Now when you don't have the cache, when you ask to read the value of x, you need to get it from the hard disk or the RAM, or it's hard. It can be RAM as well. It takes about 10 milliseconds or something. Every time you do it, you need to write it back to the RAM. So it takes 10 milliseconds. So the total is 50. But in this case, only the first time you have to get the value from the hard disk or the RAM. So it's 10. Then you take several times to store it in the several milliseconds to store it in the cache. Let's say 2 milliseconds. After that, every time you need the variable x, you can directly fetch it from the cache with a time delay of 2 milliseconds. Of course, in the last time when you want to store it back into the hard disk, you have to go back and let's say it takes longer, 10 milliseconds. So you can see there are several additional steps. Storing this value is 2 milliseconds, and also you have this separate storing step. Even so, you still have a lower duration. So the speed is high. Total time spent is low. So that is the importance of having a cache. Okay. Is it clear? Now let me show you some calculations. There are only two main equations that you need to know. First one is the cache hit ratio. Now there's no guarantee that all the values processor required is in the cache. Because cache is very small, it can store only few amount of variables, only very few variables. Right? So there can be a time the processor asks for something and it's not in the cache. If the processor asks for something and if it is in the cache, that is called a cache hit. If the processor asks for something and it is not in the cache, that is called a cache miss. Right? So cache hit ratio is the total number of cache hits divided by total number of requests made by the processor. So what do you think is the best scenario? Should the cache hit ratio be higher or should it be lower? What is better? Usually cache hit ratio is given by R. So what do you like to have? A higher R or a lower R? Okay, any other answers? What do you like to have? Higher number of cache hits or higher number of cache miss? Hit means you search for something and it's already in the cache. Miss means you search for something and it's not in the cache, so you have to go back to the RAM and retrieve it and come back. So it will take a little bit longer. So which one do you like to have? Cache hit or a cache miss? Yes, it's like a cash sheet is much better, right? You can think of it like uh, you go to the restaurant, let's say canteen. You every day order the same thing. Right? Now, as time goes by, the waiter or the cashier get used to you. So, as you walk into the restaurant or the canteen, that person had already put all the things that you usually order in a plate and ready to be delivered to you. So that way, you can access your food much faster. Right? It's like a cashier. But let's say you go there and ask for something that is not in your usual eating list, right? Not in your usual diet. Then that manager or waiter has to discard whatever he thought you might order and go back and start doing it from the beginning. That would be like a cash miss. So to get a fast access, you need to have a cache hit. So when you have a higher number of cache hits, the cache hit ratio will increase. So what is the highest number you can get for a cache hit ratio? What is the maximum number, the highest number you can get for the R? You can see the formula in this one. Yes, maximum is 1. What is the minimum one? Minimum case would be nothing is there when the process asks. Everything is wrong in the cache. You ask for something, it's not there, and if something else is there. That will be, yes, that will be 0. There's another equation that I like to present to you. That is called the average fetch time. Now remember, you can't always guarantee to have 100% cache. R will not be always 1. It's better to have a higher R, but you can't always get R equals 1. Right? So in that case, how do you calculate the average fetch time? Fetch time means the processor requests a particular variable and how long in average it takes to get that particular value. So this is the formula. So if you look carefully, you can see cache hit time and the cache miss time. Now R is the cache hit ratio. So if you get 50% of cache hits, that means 50% of the time you will only need to spend cache hit delay to retrieve the value. If you get 80% cache hit ratio, that means 80% of the time you are able to get the value with a time delay of CH or the cache hit. So let's say 80% cache hit ratio. So 80% of the time you get that part. But what about the remaining 20%? Now the remaining 20% you would have to spend time that will take to retrieve value from the storage. So the total time taken for that is called the cache miss time. So it's given here by CM. Okay. So this one gives you the time of cache hit. This is for the cache miss, and you multiply by R. So remember, R is between 0 and 1. So 1 minus R means is the ratio of cache miss. If R is 0.8, 1 minus R will be 0.2. So 0.8 times into cache hits and 0.2 times into cache miss. So that's the equation for the average fetch time, right? Now don't get confused when you say cache miss time. That includes the total time from request to retrieving the value from the RAM or the hard disk or something. The reason is to detect a cache miss, first you need to check whether it's in the cache, and if it is not in the cache, then only you have to go and fetch it in the RAM. Okay. So remember, if it is a cache hit, you have only one step. Go to cache, get it. If it is a cache miss, actually there are two steps. Go to cache and check it. Second step is to go to RAM or hard disk and fetch it back. Right? So in the cache miss, you have actually two different steps. You can't directly go to the RAM and fetch it because you don't know whether the value is in the cache. First you have to check it there, and only then you know it's not there and go back and fetch it, right? So the CM means the time for both of these steps. Checking the cache and finding it's not there and fetching it back from the some other memory storage. So let's do a small question. I hope you can see it. This is the question. Okay, can you give a try? Or shall we try something a little bit simpler? Uh, okay, we will continue this one. I see two answers are there. How about other people? Other students? Are you trying to do the question? Uh, I know it's a little bit hard as the starting question for this caching. I should have given a smaller question first and come to here. Unfortunately, I couldn't find it, and I thought this was a little bit easy. Unfortunately, a little bit harder than I intended. Not in the sense it's impossible. It's possible to do. Only things you have to have all the or both the equation in your head. Not one equation at a time. You have to have the both equation at the head. So if someone else is still trying, I can give a few more minutes. Otherwise, I can start doing the question. Maybe we'll do it together. Right? So I will ask questions and you have to give the answers. That way we can both have an interactive session. What do we know about this particular question? It says average number of requests sent by the processor is processed in 1 second is 5 to the 10 to the power 6. From them, average of 1 to the 0.5, 1.5 to the 10 to the power 6 requests are made from the RAM. Okay. Time taken to check and read a data of a single request from RAM is 0.5 milliseconds. But the average fetch time for all the requests are 0.2 milliseconds. Calculate the time taken to check and read a value from the cache, otherwise CX. Okay. Now, so the average time is given. So let's look at the equation. So average fetch time is given by R into CH plus 1 minus R into CM. So what do we know from this particular set of data? We know the average fetch time. Average fetch time is said to be 0.2 milliseconds. R, we don't have it directly in the question. CH, again, it's not given, plus 1 minus R, CM. Is the CM given in the question? Now here's the part that I think some of you might have been a little bit confused, or at least used to confuse in the paper. The question says time to get the value from the RAM is 0.5 millisecond. It doesn't mean it's the cache miss time. It means the time to get the value from the RAM into this one is 0.5. Before you can go for there, first you have to check there and go there, right? That's the two steps, right? So you have to be a little bit careful about the CM. But anyway, we'll start with here. Can we find R? So what is R? R is the cache hit ratio. So what is the cache hit ratio for this one? Can you find the cache hit ratio? Total number of requests is 5 into 10 to the power 6. And from them, 1.5 into 10 to the power 6 had to be get from the RAM. So if you are required to get it from the RAM, that means the value is not in the cache. Right? If the value is in the cache, there's no need to get it from the RAM. So 1.5 times, 1.5 into 10 to the power 6 times, you don't have the value in the RAM. That means it's actually a cache miss. So how many times do I have the cache hits? Here's the total number of requests. Total requests are 5 to the 10 to the power 6. And from them, 1.5 times, I don't get it. So that means remaining times, I should have it in the cache. So 3.5 times, I have it in the cache. And 1.5 times, I don't have it in the cache, so the total is 5 into 10 to the power 6. Is it clear to you? Okay. So now what is the R? Can you find the R? Enter the R. So you have total of this number of requests. From them, this number of times you have cache miss, and this number of times you have cache hits. So what is the R? Type the value for the R. Okay. You don't have to put it in decimals. You can put it as expression as well, because I think you will get some decimal places. Instead of that, you can directly put it as some division between two numbers. So what will be at the top? Can you remember the R equation? Number of cache hits divided by total number of requests. So how many cache hits? And what are the total number of requests? 5 into 10 to the power 6. So they cancel out. You get 3.5 divided by 5. If you want, you can cut and say 0.7 as well. Okay. What about the other one? Okay, we'll continue. So we know the R. Let's say 0.7 just in case. So what is 1 minus R? That would be 0.3. So now we know several terms. 0.2 is equal to R is 0.7 into cache hit. Cache hit means actually the CX, right? Cache hits. In the question, it says given as time to read value from the cache, that is CX. Instead of CH, we will be using CX plus 0.3 times. Here we have a small thing to think about. Now remember, the original thing is cache miss. Total time taken to get a cache miss. Now, cache miss can happen when the cache miss happens. First, you need to check whether it's in the cache. So there is a CX plus the time taken to retrieve the value from the RAM. So there will be a 0.5 as well. So here it will be CX plus 0.5. So I remember I gave partial marks for the people who forgot to put CX, but still you are almost there. Only thing is you forgot about the CX. Okay. If the question said the cache miss time is 0.5, then this whole thing is the 0.5. But the question doesn't say that. Question says time to take it from the RAM. To get it from the RAM, first you need to check it from the cache and note that it's not in the cache. So that's there. I think rest you can simplify it yourself. 0.3 CX plus 0.5 into 0.3. You get 0.15. Now, if I make some simplification errors, please let me know, right? Sometimes when we are doing the calculations, especially a bit fast, we make mistakes. I don't have calculator, right? So hopefully from this point onward, it's just simplification. So anything that there, any mistakes there, you have to do it correct. You can correct it. But up to this point, this is the theory part about the cache. Right? You start with this particular equation. You know the average fetch time. This is the cache hit ratio. So if you find the cache hit ratio, you can always find the cache miss ratio. This is the time taken when you have a cache hit. So in other words, time to get a value from the cache. This is the total time taken when you don't have the value in the cache, or in other words, a cache miss. Then you first check the cache, it's not there. Then you go there, check the value and send it back. And also store the value in the cache. So in the question, CM is not given. This is the one that we have to find. This travel time is given. So in the case of a cache hit, you have it here and go there. If it's a cache miss, you check it and then you go and retrieve it there. So CM include both CX and this retrieval time. So it gives how many times you get into the RAM. Using that, we can find the R. Once you know the R, you can find 1 minus R. And you come up with a simple equation, and solving it, you should be able to get the CX for this one. Okay, now let's quickly move to the next one. So we are running out of time. If you have any questions regarding that calculation, please put it in the chat. Right? Now, I mentioned the cache is very small. It's very fast, but it's very small. So that means you can't put everything in the cache. Otherwise, it will be filled. So you have to decide what to put inside the cache and what to be replaced. That policy is known as the cache replacement policy. So what basically happens is this policy decides what to put in cache and what to be discarded. For example, some cache policies like to keep the most frequently accessed values in the cache. For example, if something gets accessed multiple times or many times, those will be kept in the cache, others will be discarded. Some like to keep the values most recently accessed. If you recently access variable X, then the variable X might be in the cache because the cache policy thinks, okay, whatever you access recently, you might access again. Right? So there can be different cache policies. Right? So that's basically about the cache. Now I will come to the last two slides, paging and the DM is not there anyway. Paging. What the cache does is it tries to make the RAM or the main memory looks fast. So how it does is it keeps a small local copy that is fast accessible to the processor. So the caching is basically trying to make the RAM look faster. But sometimes you need to make the RAM look larger as well. Now remember, RAM is at the middle. Cache and registers at the top, hard disk and everything at the bottom. So RAM is at the middle. So how do you make RAM look large? That can happen. For example, you have a 4 GB RAM and you want to open, let's say, 10 GB MATLAB program or maybe a very large scale. So in that case, there's no way to load the whole program into the RAM because it's too large. That's where the paging comes in. So just like the cache makes the RAM faster, paging makes the paging makes the main memory looks larger. What it does is it breaks your large program or data into small chunks. These are known as page. So when the program requests particular amount of data or part of the code, that relevant chunk of the page is loaded into the RAM. Remaining pages will be in the hard disk. So as and when needed, parts of the data or the program will be loaded into the RAM. Rest of them will be in the hard disk. Now hard disk has a very large capacity, so you can store large amount of page files. Therefore, effectively the computer thinks you have a larger RAM, or effectively you can use programs that require large RAMs. Now remember, the processor doesn't know anything about this paging or caching or anything, because the virtual memory is the one that provides the information. So when you ask something to be retrieved, virtual memory has to decide whether it's in the RAM or whether it's in the page file, whether it's in the hard disk, and retrieve it and give it back to the processor. So the only difference experienced by the processor is the delay. If the file is not in the RAM, that is called the page fault. You request a particular part of the program, but that page is not in the memory, then we call it as a page fault. Sometimes you get page faults. It's not a critical issue. So if you have a page fault, you have to wait a little bit, because you have to retrieve the value from the hard disk and put it back into the RAM. So just like in the cache, you have a page updating policy as well. It's called a page replacement policy. Like in the cache, you have different policies, different algorithms to decide what the policy does. Right? So that's basically about the memory part. If I give a quick review, you have different types of memories. That's something you can go ahead in the PowerPoint. There's nothing to think too much. And you have the memory hierarchy. So this is the memory hierarchy. The idea is to make the memory faster and larger while keeping the cost and the size small. So we do it. We have smaller, faster memories and larger, smaller memories, and we connect it together. And whenever we need something frequently, we put it into cache or something registers or something that is much faster. When we want to have a larger capacity, we use paging. That means we take the memory, split into smaller chunks, and put it into the sections in the hard disk. We also have the physical RAM and the virtual memory. So virtual memory is basically, as I mentioned, it's an interface where uniform access is provided. So memory basically has an address and a data. To control the memory, you need a control line as well. So it will decide whether to read or write. Address will give you the location. Data is the actual thing that is kept written or read from the memory. The number of memory address is determined by the number of bits in the address. So if you have n number of bits, you can have 2 to the power n number of unique addresses. Each address in the memory has to be unique. And each memory address will have a location to store some bits or some data. Size of that location is known as the word size. Word size is basically a multiplier of the commonly used data types. So to get the total amount of memory, you have to multiply number of addresses by the word size. So the memory can store any type of data, including other memory addresses. If you store a memory address as its data, it's called a pointer. So pointers are commonly used in reference by when you're referenced by address kind of programming techniques. Sometimes you need to access multiple data to run an instruction. If you can access this multiple data simultaneously, it will be much faster. To support that, you can partition the memory into several banks and have a separate controller for each of these banks. So you can parallelly load multiple values from multiple banks. The virtual memory allows you to hide the complexity of your hardware. It also increases the safety and reliability of the programs. What basically happens is you have physical hardware, physical storages like this. They are going to be mapped into a virtual memory address. So this virtual memory address can then redirect it to the correct physical device. Using that, we can also have multiple programs use the same memory. For that, we will assign a separate memory space for each of the programs. The starting point of each program is known as the base, and the total number of addresses allocated for the program is known as the bound. There will be a mapping where you will be adding a constant, so the base will be different for different programs. That way, the original programs may have the same register numbers, but in the real memory, when they're accessing it, they will be mapped to a different location. because you will be adding different constants or different bases. That way you can prevent overriding and also improve the security of the given programs. The cache is the almost last thing that we learned. It's a way to make the RAM look faster. It's a small, active, and transparent automatic service. When you have a cache, your frequently accessed data is stored in the cache. So the processor can request a local copy from the cache and use it for its processing. The cache hit ratio is the number of cache hits from the total number of total number of requests. Right? When it's close to 1, that's good. When it's close to 0, it's a bad cache hit ratio. The average fetch time is given by this particular formula: cache hit ratio into cache hit time plus cache miss ratio, which can be also written as 1 minus r, into cache miss time. Remember, when you mean cache miss, first you have to check the cache and find it is not there before you can fetch it there. There are different ways to update the content in the cache. That is known as the cache replacement policy. Paging is the opposite. When you want to increase the RAM, instead of increasing the speed, you can use page files. You have a large data or program, you break into small files called page files and store it in the hard disk and upload into the RAM or call into the RAM as and when necessary. If you couldn't find the particular part in the RAM, that is known as a page fault. So I think with that, I covered most of, not most, we covered everything regarding the RAM. If you have any questions, it would be a good time to ask them.